Okay, the principle of ion exchange chromatography is based on charge difference, right? So in ion exchange chromatography, we have the abbreviation for calling cation exchanger or anion exchanger. Okay, if it's cation exchange resin, we call it as catex, means that cation and exchange, or anion exchange, we call it as annex. Okay, sometimes in paper you will see that people use catex or annex, or sometimes people call whether it's strong anion exchanger, strong anion exchanger SAX, or weak anion exchanger. So we will go into this strong and weak exchanger later. Also same with this one, strong cation exchanger or weak cation exchanger. Okay, so these are the names that usually found in the papers. Okay, so as I mentioned just now in the previous video, what is the mobile phase suitable for ion exchange is by using buffered mobile phase, or we can buffer the solution by using pH gradient from salt. As long as the mobile phase is containing the buffer, depending on what pH for certain application, you can use it as the mobile phase. Okay, again, cation exchange resin, whereby this is the name catex when you have an exchangeable cation. Exchangeable cation means that in your resin is already containing negatively charged, covalently bonded, and then you have exchangeable for example hydrogen, for example, and then when you run your analyte is positively charged, it will change this yellow hydrogen. Okay, so that's why it is called cation exchange resin. It's a bit confusing because we have two charge over here, but you have to remember on the exchangeable part here, and of course when it's positive, the ligand is going to be negative, the other way around with anion exchange resin. Okay, the stationary phase usually used in ion exchange chromatography is based on a resin we call as polystyrene, or now we have polystyrene divinyl benzene, means that the polystyrene is copolymerized with divinyl benzene, which is another polymer, so that we can prolong and extend the usage of that resin for thousands of analyses. Means that polystyrene divinyl benzene is more strong and durable. Okay, from this polystyrene divinyl benzene, if you learn from the polymerization, in polymerization we can incorporate the charge functional groups, right? Okay, we can functionalize with any functional group that we want. It either is negatively charged or positively charged. As for positively charged, we have quaternary amine. As for negatively charged, we have sulfonic part. Okay, and then the mobile phase, okay, again is the usage of buffer. This is all buffer used with salt. Okay, let's go and see how polystyrene and polystyrene divinyl benzene looks like. Okay, so this is a styrene. When you polymerize, we will call it as polystyrene. So this polystyrene framework can prepare the functionalization of the charge group. Okay, this is polystyrene divinyl benzene. So what is the difference between them? Okay, throw your answer in your in WhatsApp chat and see how you understand this polymerization. Okay, if you see from here, we will incorporate the functional groups here. Okay, so this functional group can either be sulfonic acid or quaternary ammonium ion. Okay, this is negative, this is positive. So this is only the ligand, this is not the exchangeable ions yet. This is only the ligand that is bounded to the resin first. Okay, so when you have the stationary, when you have the polystyrene divinyl benzene attached to sulfonic acid group, okay, this is what we call as cation exchange. Confusing, right? Why? Because sulfonic acid is the ligand. Okay, the name cation exchange is denoted from the exchangeable part, not the ligand. You have to understand. So, cation exchange resin will contain negatively charged ligand, and when the exchanger come, it will be positive here. This is the exchanger that can be subjected to exchangeable with your positively charged analyte. Okay, cation exchange will contain negatively charged ligand. The other way around with anion exchange resin, it will contain quaternary amine or primary amine, positively charged. Okay, so usually the resin packing is around 30 to 40 micrometer, very non-porous, because we don't need the porosity for absorption. Okay, in IEC we don't have any absorption happening. It is the electrostatic interaction only, so we don't need it to be non-porous. And if you can see, the size of this polymer is, I think, 8 to 10 times larger than HPLC. Why is up to 30-40 micron? So we go into strong and weak ion exchange. So what makes it called strong? Okay, it is called strong when you are attaching the ligand of a very strong ion. Okay, for example, sulfonic acid. Sulfonic acid, if you put in water without altering the pH, it will be charged no matter what. Just like when you compare hydrochloric acid and acetic acid, right? Hydrochloric acid will be charged immediately, it will be dissociate immediately in water, and so does for sulfonic acid. The same thing with quaternary amine, it will dissociate immediately. That's why we call as strong ion exchange. And then weak ion exchange means that it needs the pH to be dissociating. Okay, the same thing with acetic acid. Acetic acid needs certain pH to dissociate almost 100%. So the weak ion exchanger is carboxymethyl for cation, and also primary, secondary, or tertiary amines for anions. Okay, weak ion exchanger need pH, while strong ion exchanger don't need pH alteration. Okay, so this is how the strong base and weak base looks like. This is quaternary amine, and then you will have the primary or secondary or tertiary amine over here. Okay, and for cation exchanger, you will see that this is a weak cation exchanger, okay, whereby it contains the carboxylic acid, not the sulfonic. Sulfonic is the strong one. Okay, this table tabulate what is the functional group that can be attached to polystyrene divinyl benzene. So this is the functional group is sulfonic acid. Okay, therefore the exchanger is cation. That's why we see as cation over here. This is a strong one. Okay, strong cation exchanger. While this one is weak cation exchanger. You will have a cation as the exchanger over here. This is weak. Okay, this is strong just now. Okay, carboxymethyl also is a weak one, and this is a cation exchanger. Now we go to the anion exchanger. We have a strong base. Okay, quaternary amine. Okay, this is using chloride as the anion exchanger. So when you see anion exchanger, means that this is suitable for anion analyte. Okay, anion analyte. This chloride over here will be exchanged by your analyte. The ligand will stay over there. Means that when it is exchanged, when you want to analyze for next analysis, you have to generate or regenerate the ligand with new chloride. Okay, it's easy, just condition the column using chloride solution, that's all. Okay, the same thing for here. If you want the H to be here again for the next run, you just generate with acid. Okay, so this is another strong base, while the weak base is tertiary amine, and then we have also another tertiary amine. You see that the exchanger is also different. It can be different type of exchanger as well. So the resin of the ion exchange, okay, depending on the particle size, if you want to have a porous, you can have it as well, depending on your application. And the type of ion is very governing matter to use for your analysis. If you wrongly choose the type of ion, you will not see any peak. Okay, so in ion exchange chromatography, if you see baseline like this, you know already that is coming from the wrong chemistry that has been used in the first place. And purity of the resin is very important so that you won't get any ghost peak like this in your chromatography. We don't want to see ghost peak, we just want to see nice peak for your charged compound. Okay, and then you have to go and see what is the capacity of your resin. So you want to have as high as possible lah, so that it is still available after thousands of analysis. Okay, what happened when the resin has been exhaustively used? Okay, usually this column will be dumped out, and trust me, the waste is very big. So this is the drawback of ion exchange chromatography as compared to HPLC, because of the waste that will be generated from the column itself. So you can have a look again on the resin and see what is the capacity in this column. You can have a look, and what is the pH that is usable. Usually for polystyrene divinyl benzene, okay, usually it can withstand up to very acidic to very basic, because it's polystyrene divinyl benzene, because it's a polymer that can withstand pH. Okay,